All right, for our sample problems, this is question number 11. It says calculate the surface gravity in meters per second and the escape velocity for Vesta, the third largest minor planet in the asteroid belt, in kilometers per second. Okay, so gravity as usual in meters per second. The escape velocity remember the calculation is in meters per second, but then we usually change it to kilometers per second. All right. Assume that it has a radius of 262.5 kilometers and a mass of 2.59 times 10 to the 20th kilograms. All right. So for both of these, the mass is already in the proper unit. So we're good to go with the mass, right? That they're both, they're already in the proper units. All right. For the surface gravity, the radius has to be in meters. Actually, for both of them, the surface gravity the radius has to be in meters. All right. So the radius is, so this is a really simple conversion. The radius is 262.5. 0.5, and then it's kilometers, and so that has to be in meters. So of course there's, in 1 kilometer, there's 1,000 meters, right? So 10, 1,000. You could just write 1,000 like that, meters, right? All right. So the kilometers cancel, and that gives us a value. So I'm actually just gonna write this out instead. I mean, you could do it in scientific notation. That's perfectly fine. All right, so it'd be 262.5 times 10 to the third meters. Or you could write it like, you could easily do this, 262,500, right? Because you move the decimal place 3 places to the right, right? To the right. That's what that E to, oops, that's a little arrow right there. All right. So anyhow, so now we have this is of course in meters. So we have the right number. All right. So the first part, I'll call this part A. We just have to write. We have to look up the surface gravity, and so that's A sub g. The acceleration due to gravity is, of course, the value. It's here. I'll just write the equation. It's g times m, the mass of the object, divided by the radius squared. And so the mass has to be in kilograms. The radius has to be in meters. So we're good to go. All right. Let's write the numbers. So it'd be 6.67. That's what it always is for big G, times 10 to the minus 11th. Right, there's big G. And the mass of this is, what is it again? Let's see, 2.59 times 10 to the 20th. All right, kilograms, that's a 20th. And then divided by 262,500. Of course, we have to square that. Right? Don't forget to square that. That's a very common mistake, is people forget that part. All right, so here, let's do this. We'll do it over here. So 6.67 times 10. Oops. Let's go back. 67 times 10 to the minus 11th times 2.59 times 10 to the 20th divided by this number squared. So it's divided by 262,500. I mean, or you could have said 262.5 times 10 to the third. But remember, you got to square that, and then so this is the so in meters per second. It's really, remember, on the Earth it's 9.8. All right, so it's always good to compare this to what it would be. This just tells you that this is a tiny little minor planet, right? So it would be so it says to round to 2 places past the decimal. Where would my calculator go? There it is, 0.25. So it would be 0.25 meters per second squared, right? So, compared to the Earth, that's really, really tiny. And then, of course, part B is, of course, the escape velocity. I'll write it like this. The escape velocity is, of course, the square root of, so 2 times big G, which is 6.67 times 10 to the minus 11th, as it always is, times the mass, which was 2.59, that's a decimal right there, 59 times 10 to the 20th, and then we just divide by the radius in meters, so it would be 262,500. And remember, when we get the answer here, so remember, we take the square root of the whole thing, the answer will be in meters per second. Right, and then if we divide that, we divide the answer by because there's we divide by 1,000 because there's 1,000 meters in a kilometer. All right, so whatever the answer is, I'll show you in just a second. Let's do the problem. All right, so it is. Let's clear this. So it's going to be the. All right, so it's going to be 2 times 6. We'll take the square root at the end. 6.67 times 10 to the minus 11th times the mass, which is 2.59 times 10 to the 20th, divided by 262,500. All right, so that's going to equal, and then we take the square root. All right, so it turns out to be 362.7. All right, so 0.8, something like that. So it would be 362.8 roughly. I mean, I'm just, of course, that's in meters per second. And then of course we know that there's 1,000 meters in 1 kilometer. That's a K, sorry. The meters cancel. And so you divide it by 1,000, right? So this becomes, if we round it to 2 places past the decimal, it just becomes 0.36. That's perfectly fine. And that would be kilometers per second. All right, so that is problem number, what was that, 11, I think. All right, so let's try to do the next one. All right, so this one's number 12. Okay, so number 12 says an asteroid has an elliptical orbit that carries it between 0.17 and 2.47 astronomical units from the sun. So basically, here, let's draw a little picture so it comes in like this, so really close to the sun, and then it's way, way out here. So remember, what the semi-major axis is basically the halfway point. So what we have to do is we add these two together and then divide by 2. So it's going to be because on this side of the sun, it's 0.17 astronomical units plus on this side of the sun it's 2.47, and then to get what this point is right here, that you divide that by 2, and that's what we called A, the semi-major axis. All right, so let's figure out what that is. So I've added these two numbers together, and then simply divide by 2. So that's the semi-major axis. All right, so it says to round to 2 places past the decimal, so it would be the answer A. All right, so this first answer A, of course, is what was it again? I just lost my calculator. 1.32. So it's the semi-major. It actually happens to be called A. Is 1.32 astronomical units, AUs. All right, so that's fine. And then it says, so that's the semi-major axis. How often does it cross the Earth's radius in days? All right, so here's how you do part. We'll call this one part B. Basically, you have to figure out the period, and of course, because it's orbiting the sun, right? I mean, the sun's right over here, but it's still orbiting the sun. You get Kepler's third law, right? P squared is equal to A cubed. So from that, of course, P is equal to the square root of 1.32. That's a 3, sorry. But you have to cube that. All right, so here we go. And that of course gives you the period in years. All right, so we're going to figure out what the number of days it is. All right, so the fact that this comet comes within 0.17 astronomical units of the sun, and I'll maybe draw a picture in just a second. We're 1 astronomical unit from the sun. So basically, when the comet, it'll the Earth's orbit is going to be, it's almost circular, right? The Earth's orbit is going to be pretty much like this, let's say. So it's going to cross, right here and something like that. I mean, it's kind of a crazy looking drawing, but that's the basic idea. Okay, so what we're going to do is we're going to figure out the number of years. All right, so here let's just do this. All right, so it's going to be raised to the 1.23 raised to the third equals, all right, and then take the square root of that. All right, so its period is about 1.52 years or something like that. Okay, so that's the unrounded version. But really, what I need to know is how many days that is. All right, so you just take this 1.52 years and you just say, well, in 1 year there's 365.24 days. All right, and then so that, that's how many days. And the fact is, it crosses the Earth's orbit 2 times during that period. So we're going to just take this number of days and divide it by 2. That's literally the answer. Okay, so multiply this times 365.24. It's actually 2422 if you wanted to be super accurate. That's the number of days in a year. All right, so that's it. And if you divide that number by 2, right, because it's going to cross the Earth's orbit twice, right, because it comes in that close to the sun. So then it orbits the sun, once every 553.9 days. You divide by 2, and that's going to give it how often it's going to cross the Earth's orbit. All right, so we're rounding it to 2 places past the decimal. So the answer here, would be 276.96. So 276.96 days. All right, so that answers. It crosses the Earth's, this part right here, crosses the Earth's orbit every 276.96 days. All right, so that is, what was that, number 12.